Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the Seti College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And our lead story today concerns a sensational headline. Astronomers have spent a lifetime looking for the Holy Grail, and that is an Earth-like planet in outer space, a twin of the Earth. And they think they finally snagged it. What present? The planet is called Gliese 581G. It is only 20 light years from Earth. It would take a rocket ship about 300,000 years at normal velocities to reach that planet. But it seems to be in the habitable zone of the Sun. The planet weighs about 3 to 4 times more than the Earth. However, it may have liquid oceans. If it was too close, the liquid oceans would boil. If the planet were too far from the mother sun, the liquid oceans would freeze over, but it seems to be at the just right distance from the star to have liquid oceans. And liquid water is the universal solvent. It's the amniotic fluid out of which the first DNA and proteins got off the ground on the planet Earth. So the next time you look at the constellation Libra, remember that perhaps there are somebody out there looking back at you. And so today on Exploration, we're going to bring on 2 special guests to talk about life. The first is Seth Shostak. He's an astronomer with the Seti Institute, the Search for Extraterrestrial Intelligence. And he has spent a lifetime searching for signals from alien civilizations in outer space. And then we're going to bring on Ray Kurzweil, who says that, well, maybe there are going to be robotic intelligences throughout the universe. And for that matter, maybe even on the planet Earth. One day the robots will be as smart as us. And so once again, we're going to be celebrating the fact that astronomers have, for the first time in history, identified a planet that seems to be very close to a twin of the Earth, capable of supporting a liquid ocean. The next step is to verify, indeed, that it has a liquid ocean. And, of course, astronomers will then zero in on their radio telescopes to search for signals from ET phoning home. So, hold on to your hats. We could be witnessing something right out of Star Trek. Our first special guest is Dr. Seth Shostak, and we're going to ask him, what frequency do we listen on when we try to eavesdrop on alien civilizations in outer space? Where do we look?
Well, that's actually a good point because, of course, the aliens haven't sent us a fax telling us where on the dial they might be broadcasting. So you have to sort of second-guess what frequencies, what part of the dial makes sense. And that idea had already been explored, even though Frank Drake didn't know that, by a couple of guys who at that point were at Cornell University, a couple of physicists by the name of Giuseppe Cocconi, and Philip Morrison. Anyhow, these 2 guys had already thought about what frequencies make sense if you're going to send messages between the stars. And they said, well, look, there's kind of a natural answer to that because there's one frequency everybody will know, and it turns out to be 1420 megahertz on the dial. You might think, well, what's special about that? It turns out that hydrogen, which is by far the overwhelmingly most common element in the universe, hydrogen naturally emits some radio emission at 1420 megahertz. So all astronomers, of any sophistication in the universe will know about this frequency. So they said, look, that's a natural frequency. Everybody will have it marked on their radio dial. Let's try listening there. Frank Drake came to the same conclusion rather independently. And so the first experiments were done usually with a receiver that only had one channel. It could only listen to one channel at a time, just like your auto radio, and set that frequency somewhere near this 1420 megahertz magic frequency of the dial. Now, as time went on, this kind of experiment became much more sophisticated. Today, the receivers that are used for SETI listen simultaneously to tens of millions of channels at once because, you don't know exactly which frequency might be the one they're using, but they tend to look at that part of the dial around 1420 megahertz. Not always. Sometimes they'll do experiments where they're looking elsewhere, but usually you're covering maybe 1,000 or 2,000 megahertz around that frequency. So, it's a small fraction of the dial, but it seems to be a pretty good one. No one's ever come up with a better argument about where to tune.
Okay, now let's talk about Drake's equation, which is taught in every elementary astronomy course as scientists try to get a reasonable scientific estimate of the probability of intelligent races throughout the galaxy. So tell us a little bit about Drake's equation.
Well, the equation actually has an interesting history, or at least semi-interesting. Frank Drake had done that first listening experiment in the spring of 1960. So, gosh, that's 45 years ago. It was in April, I think, 1960. Anyhow, so that generated a lot of interest. I mean, he didn't find the aliens, but it generated a heck of a lot of interest. And so the next year, he had a meeting, also in West Virginia, at the observatory, in which he invited all the kind of professional scientists who were interested in this work. That total was like 10 or 12 or something. It was a fairly small number. And as an agenda, he was sitting around thinking, well, this meeting's coming up in a couple of weeks. I need an agenda. So as an agenda for this meeting, he wrote down this very simple equation, which has subsequently become known as the Drake equation. And all it does is try to estimate something called N, where N is the number of civilizations in our galaxy. Just let's confine ourselves to our galaxy that are broadcasting right now. So the number of star systems, if you will, that are producing signals now that we could detect. Now, clearly, that depends on, well, how many stars are there in the galaxy, and what fraction of those have planets, and what fraction of those planets have produced life, and what fraction of those that have produced life have produced intelligent life, and what fraction of those have produced technology, and what fraction of those are actually on the air right now. Okay, so it's a whole string of terms. There are actually 7 terms in the equation. You can find it in almost any textbook on astronomy, and that's the Drake equation. And it would be great because it would tell you, what are your chances of success? I mean, if N is only a few, then the chances that you'll find these guys is pretty small. But if N are thousands or millions or some very large number, Carl Sagan thought that the value of N was several million. Well, if that's true, then, you have a pretty good chance of tripping across a signal sooner or later. So, unfortunately, of course, we don't know what N is. There are a bunch of terms in the equation that we simply don't know. So it's more of a talking point kind of thing than it is an equation that you can actually solve or use.
And that completes the first part of our interview with Dr. Seth Shostak. He's the director of the Seti Institute in Mountain View, California. That's the search for extraterrestrial intelligence. And their webpage, by the way, is www.seti.org, SETI.org. And the other day, both Dr. Shostak and I appeared on that ABC special on UFOs. And I think it's both fair to say that Dr. Shostak and I take the opinion that the vast distances separating the stars are so huge that it would take a very advanced civilization to breach those distances. So in other words, any visitation, hypothetical or real, from an extraterrestrial civilization would reflect the fact that they are advanced, perhaps hundreds of thousands, perhaps millions of years more advanced than ours, and they would be utilizing a technology that we can only dream about on the planet Earth. Well, let's now get back with a discussion about other worlds in outer space. Just before the break, we were talking about calculating the probability of finding intelligent beings in outer space. However, there are some people who simply don't believe in the probability equations that we laid out. Other scientists say, bah, humbug. We had Professor Brownlee on our airwaves about a year and a half ago, and he said that Drake's equation is flawed. Flawed because there are new astronomical bits of information that show that, to get life is more difficult than we thought. He mentions, for example, that you need a large moon. Without a large moon, the Earth would eventually tumble in its orbit and over hundreds of millions of years, and that would make DNA impossible. He also mentioned the fact that at one point the entire Earth was frozen over. We were snowball Earth. And again, DNA would be very hard to get off the ground under those circumstances. He mentions you have to have a large Jupiter in order to clean out the debris of the solar system. He also mentions you have to be a certain distance from the center of the black hole at the center of the galaxy. Otherwise, you get fried by being too close to this very radioactive core at the center of the galaxy. But if you're too far out, then there are not enough heavy elements to create DNA and higher molecules. So, what are your thoughts? Is the Earth in some sense unique, as Professor Brownlee was hinting at, Or do you think N is quite large, as Carl Sagan believed?
Well, of course, nobody knows, so everything I'm going to tell you is my opinion on this.
Okay,
obviously.
Good enough.
If we knew the answer, we wouldn't be discussing it, but it's true. Don Brownlee and his colleague Peter Ward at the University of Washington up in Seattle wrote this book about 5 years ago called Rare Earth, in which they had indeed, as you indicated, kind of a laundry list of reasons why Earth might not be just a run-of-the-mill planet. Earth might be very, very special, so special that, in fact, although there might be some other life out there, it's not going to be very sophisticated life. It isn't going to be intelligent life. And so our SETI experiments are kind of a waste of time. That was their thesis. And since this was reviewed, by the way, in the New York Times, this book got a lot of play. And but if you actually look at this laundry list, you find that the items on it are not terribly convincing. But let's take a couple of the ones you named, for example. The fact that the Earth has a large moon, which kind of stabilizes the spin of the Earth. Okay. Now, if we didn't have that large moon, and by the way, a large moon is kind of a rare thing. You know, Mercury doesn't have a large moon, has no moons. Venus doesn't have a large moon, has no moons. Mars has a couple of moons. You could walk around in an afternoon. Tiny moons, they don't help. Earth, on the other hand, among the rocky planets, is the only one to have a large moon. Okay. And sure, it does stabilize the Earth's spin. But if you took that moon away, yes, well, the Earth wouldn't, just go completely nuts. Every now and again, the North Pole would come down to, Connecticut or some other place, that sort of thing. But it would take hundreds of thousands, maybe millions of years to do that, right? So it's such a slow event that even for complicated life like freshwater otters or whatever, right, they can just walk away from that problem. If you've got 100,000 years, before the North Pole gets to you, you have plenty of time to move. I mean, that isn't fatal to life. That's not fatal. It might be an inconvenience, if you had a society with a lot of cities, you might not want it to happen. But it's so slow. It's not fatal. Now, here's another thing in your list there. You mentioned we're fortunate to have Jupiter because Jupiter has cleaned out the inner solar system of all these big rocks that otherwise might, slam into your planet and ruin the whole day, just the way it happened 65 million years ago, taking out the dinosaurs and 75% of all other species. Well, sure. But on the other hand, big Jupiters are not rare. We know that. In fact, all the planets we've found around other stars are like Jupiter are bigger. Right? So big planets are not rare. But even aside from that, you could argue that maybe life on Earth would have gotten a little bit farther had we not had such a big planet as Jupiter out there. Because, in fact, if the dinos had been wiped out 50 million years earlier, we would be 50 million years ahead of where we are today. We'd have the cure for death, whatever. It would be, maybe we'd be better off. So I don't find that a very convincing argument. I mean, you can look at each one of these arguments. The snowball Earth, yes, there's some evidence, although it's somewhat controversial, but there's some evidence that there was a time, a few billion years ago, when the entire Earth was encrusted with ice. But there was life on Earth then. And that life wasn't wiped out by snowball Earth. It just, had to sit there and, live at the bottom of the oceans for a while. But, a lot of life, well, all life was down in the oceans anyhow. So, it didn't wipe out Earth. It wasn't fatal. Okay, so all these things, yes, they might be an inconvenience, or they might not be, but in any case, none of them stopped life on Earth. None of them stopped life on Earth. So I really don't think that Earth is really all that special.
Well, Professor Brownlee goes on, in fact, on and on and on, as I found out interviewing him. He also says that microbial life could, in fact, be quite common throughout the universe, but intelligent life, well, take a look at the dinosaurs, he says. We've had life forms with spinal cords and nervous systems for hundreds of millions of years on the Earth, but humans, only humans on the Earth, even on the Earth with such ideal conditions, it took hundreds of millions of years for humans to get off the ground. And even then, there were many times when humanity may have been wiped out. There were only a few thousand of us, 100,000 years ago to create the entire human race. The human race could have been wiped out many times during certain bottlenecks in our evolution. So he was basically saying that intelligent life is extremely rare, even if you have microbial life being common. What are your thoughts?
Well, he's right in that this is a controversial area. I think even more controversial than the question of whether you can get complex life on a lot of planets. I don't think that's so controversial myself. But just because I give you 1 million planets with life, right, and you let them cook for a few billion years, there is a legitimate question. What fraction of them will ever cook up something as clever as we are? and we are clever compared to most critters around, right?
That's debatable, but anyway.
Well, but in any case, I mean, we don't know because we still don't understand fully how, or even partially really, how intelligence evolved on Earth. What was it that produced intelligence on Earth? If it's a mechanism that was just very rare in the sense of being accidental or contingent upon a lot of special circumstances, then maybe he's right. Maybe you got lots and lots of life out there. Maybe Captain Kirk takes the Starship Enterprise out into space and finds lots and lots of life in the galaxy, but it's all stupid. Okay, that's one possibility. But on the other hand, all the studies that have been done about how intelligence arose on Earth suggest that, well, what drove it was nothing that you wouldn't expect elsewhere. And sure, it took a long time before you got this far, but you needed some preconditions. You needed warm-blooded animals with a high metabolic rate. You know, you needed all sorts of sort of biological developments. And then, in the last 50 million years, which of course is fairly short in the history of the planet, but in the last 50 million years, a lot of species have gotten smarter. Obviously Homo sapiens, but, you know, and obviously our simian relatives, right? Chimps are pretty clever. But, you know, birds are pretty clever. Even octopi are fairly clever. Whales and dolphins are fairly clever. There's been an increase in intelligence among, you know, a couple of handfuls of species in the past 50 million years. It isn't just one species that got smarter. Now, we got smarter than they did, but if you were to visit Earth 2 million years ago, you would have found that the smartest things on the planet were not our simian ancestors, but some white-flanked dolphins. They had the highest IQs, and they didn't leave a lot of literature, but, you know, they were the smartest things around. So it does seem that intelligence is actually kind of a fairly natural product of evolution once you get to a certain level of complexity. This is controversial, but at least the indications are that intelligence is not some sort of miracle.
Okay, well, shifting gears a little bit, we also had Professor Dan Wertheimer from the University of California at Berkeley on our airwaves a few years ago, talking about Seti at home. That is, on your home PC, you can get a chunk of this radio data and have your PC, via its screensaver, basically crunch some of the numbers to look for intelligent signals. What's been the progress for Seti at home in the last several years?
Well, Seti at Home was intended originally just to be a very short-lived project, maybe for a year or two, but it was so popular that it's continued. They expected, you know, maybe 50,000 people, would download this free bit of software so that when they walk away from their computer, you know, it's still humming away, that it would process a certain amount of Seti data that it would download from the servers at the University of California at Berkeley. Well, more than 5 million people have downloaded that software, So that's, that's 100 times as many as they expected, and about a third of them use it at any given time. What they do is they distribute a little bit of the data they collect from the radio telescope down in Puerto Rico, the Arecibo radio telescope, which a lot of listeners may have seen in the movie Contact, movie GoldenEye. You know, it's a great movie star. Yeah, they distribute about 1 or 2% of the data they collect there on the web for people using the screensaver. But the point is that there are so many people doing this with their home computers that it is by far the largest computer project, the largest computer, if you will, in the world right now. And those data are looked at extraordinarily carefully. So, you know, it's really a very, very fine-tooth comb. They look at all the rest of their data right there at Berkeley using, you know, the local Berkeley computers, but they can't look as carefully as they can at this small fraction of the data, which, you know, are the prime data, if you will. Now, has anybody found something? Well, people find stuff all the time, of course. If you do this sort of work, and you're using a big antenna like the one in Puerto Rico, you find signals all the time. That's right. You got this huge antenna. It's connected to a receiver that has millions of channels. Of course you pick up signals. But, of course, the question is that ET on the line or is that AT&T on the line? Is it just interference from a telecommunications satellite or something like that? Now, what the guys at Berkeley do is they look at all the signals that have been found by people using their computers at home. And they look for those cases where a signal has been found more than once, in fact, more than twice. If a signal has been found 3 different times, right, not just by 3 different people, that doesn't count, but by, you know, at 3 different times. In other words, the telescope was pointing at some spot on the sky and they find a signal, and then, you know, 3 months later comes back to that same point. And somebody else finds it again at that same frequency, at that same spot on the sky. If that happens 3 or more times, then they say, hey, look, that's, you know, kind of interesting from a statistical point of view. That suggests it's not just a noise spike. It looks like a real signal. And then they will go down to the telescope and will deliberately look at that spot on the sky for a long period of time, for a few minutes, whatever it takes, and until they can verify whether the signal is still there. They have done that on several occasions. So far, no dice. But on the other hand, it is quite possible that somebody running SETI at home could, in fact, find the signal that would entitle them to pick up a prize in Stockholm and have dinner with the king.
And that, of course, would be perhaps one of the pivotal events in human evolution on the planet Earth.
I think so.
Well, let me ask you now the $64,000 question. What do you, as an individual, think N is, N being the number of intelligent planetary systems out there, and where are they?
Yes, well, of course, I don't know what N is either, but I tend to agree with Frank Drake, who still works here at the SETI Institute. His office is down the hall from mine. And Frank is now, I guess he'll be 75 in another month or so. But he's still as active as he ever was. And he's a pretty smart guy. He's one of the cleverest guys I've known. And if you ask Frank, look, this is your equation. What do you think Ed is? He'll say, well, I think it's probably around 10,000, which is kind of a conservative number compared to Carl Sagan, who thought it was a few million. I think Isaac Asimov thought it was 2/3 of a million. So Frank is saying about 10,000. Well, if it's anywhere between 1,000 and, well, some bigger number, if it's more than 1,000, then that means that the nearest aliens are within, on the order of 1,000 light years, okay, to us. Now, keep in mind that if you look at the whole Milky Way galaxy, it's about 100,000 light years across. So this is, only like 1% of the way across the galaxy. 1,000 light years. That's far if you're trying to drive it in your Honda, but it isn't so far for a radio telescope. If that's the case, and it really is, it's up for grabs. Obviously, we don't know. But if that's the case, then our experiments should find a signal within the next 20 years, because within the next 20 years, we will have kind of searched stars out to that distance. So that's my bet. But on the other hand, we're not going to know the answer until we know the answer.
And what are your thoughts about, well, where are they? SETI so far has picked up nothing. Is that just a question of lack of sensitivity of the SETI antennas, lack of detectors, or is it because they're shy out there in outer space, or maybe they don't exist? Or, well, what are your thoughts about why we haven't picked up any messages yet?
Yeah, well, this I think that the answer is very simple. I think it's simply because we've not combed enough galactic real estate yet. But, there are people who say, no, the fact that you haven't heard anything yet means something. It means that they're not out there, because any society that was more advanced than ours, and most of them are going to be more advanced than ours. I mean, if intelligence really does occur on planets in a fashion that's not extraordinarily rare, then most of the societies out there will be much older than ours, because, after all, we're the new kids on the block. The Earth has only been here for 4.5 billion years. The galaxy's been around for like 3 times that length of time. So most of the stars out there are older than the sun. So if they're really advanced, then they should have been able by now to maybe colonize big chunks of the galaxy. Who knows? They should have been able to spread around. They should have, remote transmitters. They should be very easy to find, right? And the fact that we haven't found them sounds like some sort of paradox. In fact, this little argument is often called the Fermi paradox, because Enrico Fermi, the physicist, the Italian-American physicist, was the first to point this out over a lunch at, I think it was Los Alamos in 1950. But in any case, that's his argument. I don't think I buy into that. I don't think it's a matter of them being shy, being coy. Maybe some of them are shy. Maybe most of them are shy. But if only one society has a powerful transmitter out there, then we have a chance of success. I think the reason we haven't found them yet is that we haven't looked very carefully. And all of that is going to change in the next few decades, mostly because of the march of technology.
Well, my personal point of view is that if there's an anthill in the country and you're walking down this country road and you bump into this anthill, do you go down to the ants and say, I bring you trinkets, I bring you beads, I bring you nuclear energy and DNA technology, or perhaps maybe you step on a few of them?
Yeah, probably. I get phone calls just about every other day from people who have their own explanation of why we haven't heard anything, and it's usually because the aliens are put off by our environmental degradation and our, threatening one another with war and all that sort of stuff. Indeed, I think that from their point of view, none of that matters terribly much any more than whatever wars the ants are getting into concern me. They don't.
Mm-hmm. Now, another stream of thought says that we're looking in the wrong place. For example, take a look at email. Email is compressed, email is broken up and goes through many cities and then recombined at the other end. So if an alien civilization had even a primitive email system, and we were eavesdropping on it, we wouldn't hear much at all. The signals would be compressed in a way that we don't understand. They'd be fragmented and redistributed and reassembled someplace else in a code we don't understand. So we could be listening in to messages that are teeming with intelligent things in it, but we are simply too primitive to understand it. What are your thoughts about that?
Well, I'm sure there's a lot of truth in that. I don't expect that we are going to understand any of the messages, even to the point of being able to sort of break them up into the bits that that make them up. And it's also true that, there are all sorts of methods for encoding information, for sending bits around that are fairly sophisticated that we use. For example, your cell phone tends to use what is called spread spectrum technology, where the signal is spread all over the dial instead of being concentrated in one spot. That's very hard to find with a radio receiver unless you know all the details of their communications schemes. So, yeah, there are lots and lots of ways they could make the signal hard to find, but in the end it comes down to this. If they have a transmitter on, that puts a certain amount of energy somewhere in the radio dial, somewhere in the radio spectrum. And we don't worry about how it's encoded or what the message is or anything like that. We don't worry about the message when we do our SETI experiments. We're just trying to determine, is a transmitter on? We're looking for narrowband components to the signal. It's called little, lots of excess energy, if you will, at certain spots on the radio dial. If we find that, we, of course, don't know what they're saying, whether it's something profound or whether it's something trivial like used car ads. We don't care about any of that. We're simply looking for evidence that their transmitters are on because, after all, that's the proof that we're after.
Okay, now let's talk about flying saucers. Of course, the distances between stars are enormous. It would take the Voyager spacecraft thousands and thousands of years to reach the nearest star. But that's because, we're kind of primitive on this scale that we're talking about. Another civilization could easily be 1 million years ahead of us. And so the next question is there a law of physics preventing a civilization millions of years ahead of us from making contact with us? Is there any brick wall that prevents an advanced civilization from making contact?
Well, Michio, you're the physicist, and you know that there isn't. There's no physics that prevents it. Now, there may be some physics that makes it very hard. Conventional physics, if you use, rockets in the normal sense, the problem there is our rockets, of course, don't go fast enough. But, they're more advanced. They can build better rockets. But when you get up to very high speeds, and you really do need speeds that are comparable to the speed of light if you want to get from one star to the next in less than a century, which sounds to me like something you might want to do no matter who you are.
Well, I'm afraid that's it for the first part of Exploration. Our next guest is inventor Ray Kurzweil, who is an authority on the theory of robots, who's convinced that we are, in some sense, creating our evolutionary successors on the planet Earth. Think about that. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. In the first half of Exploration, we began a discussion with Dr. Seth Shostak. He's the director of the Seti Institute in Menlo Park, California, perhaps the principal organization on the Earth that is seriously trying to intercept signals from outer space sent by advanced civilizations. And even though so far they haven't picked up any signals, they do hope that a recent influx of money from the billionaire from Microsoft, Paul Allen, may hope to rejuvenate the fortunes of the Seti Institute. And in the second half of Exploration, we're going to bring on inventor Ray Kurzweil, author of a number of bestsellers, including The Age of Spiritual Machines and The Singularity is Near. And his thesis is a controversial one. It's a minority opinion, but it's an opinion that has to be heard. And his claim is that very soon, perhaps by 2020, perhaps very soon machines will begin to approach human intelligence and perhaps even exceed human intelligence. And even worse than this for humans, robots will be able to create copies of themselves that are even more intelligent than they are. And so they'll be able to bootstrap themselves to become arbitrarily intelligent, in which case they may begin to leave the Earth and begin to colonize the galaxy. That is called the singularity, the point at which we have runaway machines creating machines of even higher intelligence, and the whole process just keeps on going until they, well, take over the universe. Sounds like science fiction? Well, yeah, but it's a position that can't be ruled out. So once again, our special guest in the second half of Exploration is inventor Ray Kurzweil, and we are talking about, well, what happens when the computer revolution goes amok? Mr. Kurzweil, the first question for you is, how did you first get interested in robots and artificial intelligence?
I've actually had mine being an inventor since I was at the age of 5. And age of 12, I discovered computers. I built some primitive computers myself and got access to one as part of a summer job, and quickly became fascinated with the ability to kind of model the world, albeit primitively at that time, in the computer and create virtual realities, and also model our thinking processes. Quickly became interested actually in pattern recognition, which is my view is the fundamental basis of human intelligence rather than logical, sequential, analytical thinking. And a project I did in high school was to build pattern recognition models of melodies, and I would feed in the melodies of Mozart or Chopin, and it would build a pattern recognition model and then write original melodies in the same style from that model, which were recognizable, kind of sounded like second-rate compositions from a second-rate student of Chopin or Mozart. And that started really a lifelong fascination in pattern recognition, which is really my primary technical field.
Okay, and let's talk about your book, The Age of Spiritual Machines. First of all, what is a spiritual machine? Is that a contradiction in terms?
The primary concept of spirituality is really consciousness. If we consider a being or an entity to be conscious, then we consider it to have spiritual value. And if you look at all the different religious traditions, what they really mean by a soul and by spiritual reality is consciousness, an entity that really has subjective experience and can feel pain and joy, as opposed to just the conventional concept of a machine, which is operating by some kind of automatic process. And we don't worry much today about causing pain and suffering to our computer programs. But our computer software is still millions of times simpler than the human brain. We do find, if we look at the human brain, that we actually can model it with great precision neurons and even substantial clusters of neurons. We can talk more about that. And we will have machines, which is to say non-biological entities, that do have the complexity and richness and depth of the human brain, indeed modeled on the principles of operation of the human brain within a few decades. And when these entities claim to be conscious, to be joyful, fearful, angry, and so on, unlike, let's say, the computer characters in video games today, those entities a few decades from now will be as convincing as humans. They'll have all the subtle emotional cues that we associate with somebody really having those subjective experiences. So are they conscious? Some philosophers will say no, they're not squirting human neurotransmitters. You can't be conscious if you're not biological. But there won't be any clear distinction. We won't be able to separate them from any kind of objective observation. And my prediction, and this is really not a philosophical statement, but a psychological and political prediction, is that the bulk of humans, unenhanced humans, will consider these non-biological entities to be conscious. In any event, they'll be very intelligent. They'll be able to convince us that they're conscious, and they'll get angry at us if we don't believe them. And it'll be an actual political and legal issue as well. in my view, the real issue of consciousness is not something we can resolve scientifically, because science involves third-party objective observation. Consciousness is inherently first-party subjective experience, and there is a gap there. Some people go on to say, well, since it's not scientific, it's not an important question. I would turn that around and say it's really a very fundamental question. It shows that there is a need for philosophy outside of science. But these will become real compelling questions as opposed to just abstract philosophical debate in this 21st century.
Okay, and let's talk about the past first as a guide to the future. Back in the 1950s and 60s, there were dazzling breakthroughs in artificial intelligence theory. We had the first machines, for example, that could play chess and checkers, not very well, but they could at least play the game. They could solve simple algebra theorems. They could even play doctor to a degree and do simple diagnoses. And there were all these fantastic predictions that just within a few years, humans will be put in a zoo. We'll all be zoo animals, and our creations will throw peanuts at us and make us dance behind bars, because look at how fast computers are learning. And then there was the movie 2001, and, well, the year 2001 came and went, and we still do not have the robot Hal, the murderous robot in Arthur C. Clarke's famous movie that could pilot a spaceship, could play chess, and interact with humans as if it was a human itself. So the question is, what happened to the dream of the 1950s and 60s when everyone was predicting that humans would be obsolete by the 1970s?
Well, your observation is correct. I would say wasn't everyone predicting that. There were some famous predictions from Simon and Newell at Carnegie Mellon, which came into disrepute. But there was over-optimism because machines were doing adult activities, like solving some unsolved theorems from Russell and Whitehead, and doing these adult activities, playing chess, in some narrow cases making medical diagnoses as well as doctors and so on. So it seemed it wouldn't be long before a computer could do everything. Another 10 years went by, and we realized that computers, while they were able to do these high-level analytic tasks, were not able to do something that a 4-year-old can do, which is, let's say, tell the difference between a dog and a cat or recognize faces. And this is really a fundamental issue, in my view, that the fundamental basis of human intelligence is not analytic, logical thinking. And, in fact, machines can do that a lot better than humans in most cases. The fundamental basis of human intelligence is pattern recognition. We can see that in the contrast with how machines play chess, which is this minimax combinatorial expansion of move, counter moves, which it does largely through brute force. We can look at millions or even hundreds of millions of board positions in a second. Kasparov says he looks at less than one board position in a second, but humans use their tremendous powers of pattern recognition to recognize situations they've thought about before. And we don't think fast enough. Our interneuronal connections compute 200 calculations per second, which is about 10 to 100 million times slower than electronic circuits, but we have 100 trillion of them, all computing simultaneously, self-organizing. Information is really represented as a pattern. No key connection is all that important. It's a very different paradigm from computers we're used to, and it's a very good architecture for recognizing patterns in a profound way. That is really the heart of human intelligence. Now, we have been making steady progress in pattern recognition. I could give many examples of that, both in terms of recognizing language and speech. Character recognition have all improved gradually. Even in chess, machines have become better qualitative players. So you have Deep Fritz and the current programs working actually as well as Deep Blue, despite the fact that they're about 100 times slower, because they're doing a better job of pattern recognition. So we are making steady progress on that, and that is really the key issue now. And part of the guidance we'll get in terms of creating the templates of human-level pattern recognition is to actually understand how humans do it, which brings up the issue of reverse engineering the human brain. It wasn't long ago before people were saying, well, our intelligence is just below the level necessary to actually understand our own intelligence. But what we're finding is that as we're able to actually instrument the brain and see what's going on, and our ability to scan the human brain and to actually see the connections and the firings of neuronal connections and synapses is increasing, actually doubling every year, we are able to develop very detailed mathematical models of neurons and neuron clusters. Lloyd Watts and his colleagues have actually created a reverse engineering of the whole acoustic area of the brain involving 12 different regions with a great deal of detail, have re-implemented that in software and submitted that to psychoacoustic tests, which performs very comparably to human auditory perception. If you follow all the exponential trends in computation, communication, brain scanning, exponentially growing knowledge of the human brain, it's, I think, conservative to say we will have reverse engineered the principles of operation of the human brain within a quarter century. And that will provide us more powerful biologically inspired methods for pattern recognition.
Okay, well, we've had several AI specialists on the radio show before, among them Rodney Brooks of MIT, the director of the Artificial Intelligence Laboratory. And I asked him a key question, and that is, well, how powerful are the MIT robots? And he was very proud to say that he's the godfather of the Mars rover, an advanced robot which actually wandered on the surface of Mars. But he was honest and said that his most advanced robots have the intelligence of a cockroach. In fact, cockroaches do it a lot better, he said. Cockroaches can scope out environments, see obstacles, boulders, maneuver around them, and they're quite good at this. And robots at Carnegie Mellon and Stanford, well, when they walk down the hall, it's lucky if they don't gouge out a piece of the wallpaper when they walk down the walk down the hallway. So how smart are our robots? Are our robots really so dumb that they are really insect level at the present time, barely able to understand chairs, tables, the ceiling, the roof, people maneuvering around the room? How smart are the robots today?
Well, robots and artificial intelligence in general are operating far below biological levels, both in terms of hardware and software. And I think it's worthwhile talking about both of those, but also to understand that we're making exponential progress in both of these realms. And exponential progress really sneaks up on you. And just to use an analogy, Kasparov played the best machines in the 1990 at chess, and they were pathetic, and he scoffed at them. And it was just inconceivable that they would ever reach his level. But they gradually got better. They're doubling in performance every year, gaining 40 chess points every year, and chess scale is exponential. And then they surpassed him, operating at or beyond his level by 1997. We'll see the same thing in other areas. And it's easy to lose sight of tremendous power of exponential growth. We are doubling computation at least every year, and we'll talk a little bit later about the issue of Moore's Law, but I believe that this phenomenon will continue past Moore's Law into three-dimensional computing. And in terms of software, we're making exponential progress, as I mentioned, in understanding and reverse engineering the principles of operation of the human brain. There's a new brain scanning method now that's being developed, which will be available within a couple of years, that will actually be able to see individual nerve fibers firing in a cluster of thousands of neurons at very high resolution, very high resolution also in terms of time scale, which will really give us the means to reverse engineer those circuits. I mean, so far, we've been really unable to see what's going on. It's very hard to diagnose a circuit if you can't instrument it, but if you can put sensors on in the right place and see what's going on, it's very straightforward to reverse engineer. The human brain, of course, is created by a genome that doesn't have very much information in it. Even though the human brain itself appears to contain thousands of trillions of bytes, the genome only has about 12 million bytes of information to characterize the initial design of the brain, because there's a lot of random wiring in the way it's actually constructed, which then self-organizes to reflect its experience with the world. So the principles of operation are of a complexity that we can't understand. And that will provide us at least biologically inspired paradigms for the software of intelligence. And so the capabilities of all of these systems will improve quite steadily, and we will master different levels of biological intelligence. Ultimately, I believe within less than 3 decades, by 2029, these machines will be operating at human levels and will combine human levels of intelligence, the subtlety and suppleness of human pattern recognition with some of the natural advantages of machines, most notable of which is the ability to instantly share knowledge.
Now let's talk a little bit about Moore's Law, the doubling time you mentioned of 18 months for computers, meaning that at Christmas time, your computers are almost twice as powerful as they were the previous Christmas. Exponential growth in bacteria, for example, eventually seals off, otherwise bacteria would take over the entire planet Earth. And exponential factors do taper off because of external effects. Now, with Moore's Law and computers, the engine driving Moore's Law is ultraviolet etching technology, by which we can etch tinier and tinier transistors on a silicon wafer the size of your thumb. But eventually the transistors get so tiny, you get the quantum theory. And at that point, you get short circuits. Leakage takes place. All hell breaks loose. And by 2020, all bets are off. The Intel, one of the senior engineers at Intel, admitted recently in a major paper that, yes, they can see the end of the tunnel. And that is, at a certain point, it's going to be prohibitively difficult to etch silicon components that are tinier and tinier, and eventually you get leakage because you don't know where the electrons are. Some people have said, let's make three-dimensional cubes. But the problem there is you have heat generation, enormous quantities of heat generated in three-dimensional cubes. So the question is, what happens after 2020 when all hell breaks loose and Silicon Valley becomes a rust belt?
Well, it's a key question, and to examine that, I've done a number of things. I have been an ardent student of technology trends. I've been measuring the actual power of different technologies for 25 years. I have a team of people doing that. One thing I did is put 49 famous computers over the last century, long before there was a Moore's Law, on an exponential chart. And this exponential growth has been going on not just for Moore's Law, but back through 5 different paradigms. Moore's Law, the shrinking of transistors on a flat integrated circuit, was not the first, but the 5th paradigm to provide exponential growth to computing. And every time one paradigm ran out of steam, because as you correctly point out, every method of exponential growth eventually runs out of capacity. Rabbits in Australia eat up the vegetation and stop growing exponentially. They even reverse direction. Every time that happened, another paradigm came along and started another S-curve of exponential growth. They were shrinking vacuum tubes to continue exponential growth. Finally, they couldn't shrink them anymore and keep the vacuum. That paradigm ended. Transistors came along. And the next paradigm will be three-dimensional computing. We live in a three-dimensional world. Our brain's organized in 3 dimensions. Our brain, by the way, uses a very cumbersome, very slow electrochemical information processing method. That's 200 calculations per second. They're digitally controlled analog transactions, but they're roughly comparable to calculations. At least 10 million times slower than electronic circuits, but it gets its tremendous power from the fact that it's organized in 3 dimensions. Now, the brain itself is an existence proof of the feasibility of organizing circuits in 3 dimensions and dealing with the heat problem. I proposed 3-dimensional computing as the 6th paradigm to replace Moore's Law, which was the 5th paradigm in my book, The Age of Spiritual Machines, 4 years ago. It was considered a radical notion then. I would say it's much more of a mainstream expectation at this time. There's been tremendous progress in building working 3-dimensional circuits over the last 4 years. There's been a steady flow of breakthroughs, including conceptual examinations of this thermal issue that you alluded to. And there are ways of designing the circuits in porous ways to deal with the heat issue. 1 watt of power, which would not generate that much heat, would be sufficient to emulate human brain capacity. in a cube that would be very tiny. So the thermal issue is, in fact, a key challenge, but there's a lot of confidence that that's feasible. And we still have at least a dozen years to go. And what we've seen typically is when the end is in sight for a particular paradigm, it creates tremendous pressure in the R&D community to create the next paradigm. And we have a lot of advance warning this time. And already, in fact, just using conventional lithography and going to the third dimension, because after all, even conventional circuits have 14 or 15 layers of material, so they do have some three-dimensional capacity. And there's been successful efforts to build circuits with dozens and even up to 100 layers of circuitry just using conventional techniques. There are many different approaches. The most effective appears to be carbon nanotubes, which is what I had predicted in my book 4 years ago.
Okay, well, the heat problem, as you mentioned, is quite fierce. Engineers tell me that very soon, even cubicle computers will generate so much heat you can fry an egg on them. Let me ask you a question about the the top-down approach and the bottom-up approach. When we had Rodney Brooks on the radio, he said that there are two approaches to artificial intelligence, top-down and bottom-up. The top-down approach has dominated AI research for the last several decades, and the goal there is to have a CD-ROM with all the laws of common sense, all the laws of logic on it. You simply put the CD-ROM in a computer, and all of a sudden your computer says, I think, I am aware, I am conscious, okay, I'm alive. That's the top-down approach, which failed rather miserably. We know that there are hundreds of millions of lines of common sense. We can't put them on a CD-ROM. There's so many of them. The other one is a bottom-up approach, which follows nature, Mother Nature, allowing machines to learn like bugs, like infants, to bump into the environment. And that approach is like a neural network approach. So could you explain to us a little bit about neural network theory? And this, of course, means that our brain, in some sense, is not really a digital computer at all. That perhaps we were sort of misled over the last 50 years in terms of the successes of silicon, but the brain is really a neural network and not really a Turing machine at all. Could you elaborate?
Well, I've always been a strong advocate of what you're referring to as the bottom-up approach. As I mentioned earlier, the brain, the design of it, characterized by only about 12 million bytes of compressed information in the genome. You might wonder, how could that be when the brain itself contains millions of times more information than that? And the way it works is the genome specifies a particular design, but in a particular region, the actual wiring of the connection is random within certain constraints. And we know that that's the case, having watched how that process unfolds. Then there's actually kind of an evolutionary process where the connections that make the most sense in the environment survive. And it's actually twice as many connections in the newborn baby's brain as exist a year later. There's a lot of self-organization. And the brain has the capacity to interact with its environment, make sense of the environment, as well as make sense of its own design and its own interconnections actually continually being repruned and reconnected to make sense of the environment and to learn. And that is really the only approach that's going to work. I think the Psych project of Doug Lynott is interesting. It's accomplished a lot, but I never felt that we could build human-level intelligence that way. We really have to build it the way nature builds it, which is a machine that has the capacity to learn, and then provide for its education. Now, neural nets is sort of one attempt based on a crude model of how human neurons work, which actually builds lots of neuron simulators and connects them somewhat the way the brain connects them and let them self-organize. And there's a number of different approaches to neural nets. They're all very simplified from what we now know is true of actual neurons. And as progress in reverse engineering the human brain progresses and we have more sophisticated and realistic models of actual neurons, we can build more realistic biologically inspired paradigms. But in general, pattern recognition, which is my field, works by emulating nature in these self-organizing methods. We set up some approach, which could be a neural net, this thing called Markov models, which is the mathematical cousin of neural nets. There are evolutionary algorithms that actually emulate evolution. And actually part of human learning has a kind of an evolutionary process take place inside the brain for the better connections that survive. And we use these techniques in our pattern recognition approach. They'll actually simulate evolution, have different solutions to a problem, compete with each other through thousands of generations of simulated evolution. And these biologically inspired methods are very powerful. They give results that are essentially unpredictable, just as sort of human decision-making is unpredictable without actually letting it unfold. And this is really the approach that will work. Trying to define as analytic, logical rules every bit of common sense, it's not going to work. It's too complex, too unwieldy, and it's not how human intelligence works.
And that concludes our interview with inventor Ray Kurzweil, author of The Age of Spiritual Machines and The Singularity is Near. Well, before you start to write off humanity in the dustbin of history, realize that there are numerous barriers to reaching this singularity. And one of them is the fact that Moore's Law, that is the idea that computer power doubles every 18 months, well, that can't go on forever. In fact, by 2020, we're going to see a serious dent in Moore's Law because silicon power cannot sustain ever-increasing speeds. First of all, you have heat generated, so much heat you can fry an egg on a chip. And second of all, worse than that, you have leakage because of the quantum principle. Components will be so small that because of Heisenberg uncertainty, you don't know where the electrons are anymore, and they leak out of the wires, they leak out of the layers. As a consequence, we physicists are trying to create the next generation, meaning quantum computers and molecular computers, but quite frankly, they're not ready for prime time. In fact, we physicists don't know if there's going to be a replacement for silicon. So if Moore's Law begins to flatten out, perhaps there's hope for humanity. Well, I'm afraid our time is up. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics, and you've been listening to two interviews today. In the first half, we listened to Dr. Seth Shostak, a director of the Search for Extraterrestrial Intelligence, the Seti project based in Mountain View, California. And in the second half of Exploration, we listened to Ray Kurzweil, an inventor who is firmly convinced that the age of robots is coming, and it's only a matter of time, perhaps sooner than later, when machines become conscious and more intelligent than us. Good day.